I'm Brad Chen in the System Infrastructure Group, and I'm pleased to introduce Manish Fakharjani, who's going to tell us today about work happening in his research program in Colorado on finding opportunities for threaded level parallelism.
Okay, great. Thanks for the introduction, Brad. So hopefully I have something interesting to tell you guys. I know Google has a ton of smart people working internally on lots of interesting stuff, and you're very secretive, so we don't actually know exactly what's going on the outside, so it's hard to tailor a talk for the audience since it's not, as I said, it's not entirely clear exactly where your problems are. But hopefully I have something interesting of interest to say to you. So today I'm going to talk about finding parallelism from finding opportunities for parallelizing otherwise sequential applications. And so this is work that's done in my research group. Generally, I would have my students present, but the student whose work I'm focusing on today isn't here, and so I apologize for that. But this is work that's done in my group and with my students, Brian Bushnell, John Giacomoni, Graham Price, and Rohan Ambli at the University of Colorado at Boulder. So let's get started. All right, so I come from an architecture background, and so every architecture talk has to have a Moore's Law slide. And so we'll put up the Moore's Law slide, but there's something interesting, right, that's happening in our community. And so most people, when they think about Moore's Law, think, well, you know, computers get faster at some exponential rate. But the truth is, Moore's Law is a statement, it's an economic statement that says that the economics of the semiconductor industry will force fabricators to integrate more and more transistors at an exponential rate. And the rule of thumb has been about every 18 months you can expect the number of transistors on a die to double. And that's held remarkably true if you look at this map of, say, Intel microprocessors from here to 2000. And you'll have to take my word for it, but this exponential trend continues. Oh, and it's exponential because our vertical axis is logarithmic. So then, if you look, what we're used to is what I'll call Moore's corollary, which is that performance also doubles every 18 months or so. So those transistors are converted directly to performance. And this is held remarkably true. This is the fastest SPECint performance reported in each quarter starting from '99. The red line is the red line that you see up there is the ideal curve. And the other lines are the actual reported for SPECint and SPECfp, right? The green is SPECint and the gray is SPECfp. So if you look at this, what's happened is sometime around Q3 of 2003, we fall off this Moore's corollary curve. And so there's a gap here, right? So we see that there's a substantial gap. And so this is the gap that we're trying to fill. So why have we fallen off the predicted performance curve? Well, the reason is because designers around that same time frame stopped building uniprocessor systems. And basically, if you look at high performance systems today, uniprocessor systems are at the end of their life. So we're now, everything that you buy for your desktop is basically a chip multiprocessor. My laptop has 2 processors in it, right? 10 years ago, you'd say, oh, you'll have a dual processor laptop. What? Right? But now I have a dual processor laptop. You can buy a 4-processor workstation from Apple for under $3,000. So multi-cores are here, and we're talking about a large number of cores, right? We're at 4 cores now. MIT group has fabricated a 16-core machine, and Intel has an 80-core prototype. So we're talking about hundreds to maybe thousands of cores, so going from multi-core to many-core. So the problem for us, unfortunately, is that everything that we do in architecture to support the application on the silicon is based around the von Neumann architecture. So we have a von Neumann programming model. We have a von Neumann compiler. The operating system is designed to really multitask and time share a von Neumann processor, a von Neumann applications on a von Neumann processor, though it is a little bit more sophisticated than that today. But the architecture is von Neumann, so on and so forth. And what we've done is the architects have said, oh yeah, well, we no longer know how to make that von Neumann thing go any faster. So now we're going to build these shared memory multiprocessors. Go deal with them. Well, this is a difficult problem because everything else in our stack is centered around von Neumann architectures. And so you can say, well, all right, I'll just keep the von Neumann programming model and I'll just build a new compiler and everything will be good. But as we know, there's been about 30, 40 years of, maybe 30 years of research in this area. And we've not been able to successfully produce a compiler that can parallelize these applications, right? And so we break this chain, right? We have no way to get our von Neumann applications onto these shared memory multiprocessors. Furthermore, operating systems are not very good at dealing with 400 cores. You know, even 100 cores, 64. If you look at a lot of things in Linux, for example, right now at about 16 or 32 cores, you start to run into some scalability problems on these systems. And so we have to adapt the operating systems as well. Some of these things we know how to fix, we just haven't fixed them. Other things we don't know how to deal with. Okay, so the von Neumann programming model is not an option. And we have to replace it. And the best thing that we know what to do so far is say, well, okay, now you have a shared memory multiprocessor programming model. Great. The problem that we have with that, if the next slide will come up, the basic problem with the shared memory multiprocessor programming model is, well, programmers are really bad at explicitly parallel programming. Okay, now, and you've seen this internally, right? So there's internally, there was that famous MapReduce paper that you guys published, right? And so this is a way to sort of structure parallel programming so that people can do it even though they're bad at the problem in general. So if we look at this, programmers are much better at sequential programming. It's not perfect, as we know. A lot of these things have bugs. And our current solutions haven't worked, right? The solution to this has typically been, let's hide the parallelism and build a compiler. And as I mentioned earlier, this hasn't worked. Okay. So what do? Right, when we move to these multi-cores? Well, you say, well, at Google, we have parallel apps, and we have MapReduce, and we do these things, right? And so right now, each of these boxes, which is one of the functions applied to one of the datums in the map process, you map it to, say, a cluster node. And you say, well, now what happens when our nodes become multi-core? Oh, well, all I'll do is I'll say 2 cores. OK, I'll put 2 of my map nodes. I'll take 2 of those maps and put them on 2 cores. 4, no problem, right? But you know, as this gets bigger, this isn't really going to work very well. You still only have 1 disk, you still only have 1 memory channel, so on and so forth. And so as these things scale, this may not be the best way to take advantage of these applications. Second of all, this doesn't necessarily help you with the latency of anything, right? It might allow you to reduce your utilization or something like this, which is useful. But it doesn't necessarily accelerate the amount of time each of those map nodes takes. So when you look at using multi-core systems and parallelizing things, there are different ways to think about parallelism, right? There's the classic task parallelism. I'll run 2 different applications in parallel on the machine, no data communication whatsoever, right? So that's the classic task-based parallelism. Then there is data parallelism, which is exemplified by web serving, and MapReduce is in some ways an instance of this where you fan out your data to a whole bunch of nodes, you do a whole bunch of computation, and then you recombine the results at the end, right? So this is like the split join and these types of semantics, right? And then there's another type of parallelism which we often don't think of, and it's been a large portion of focus in our research, which is pipeline parallelism. And we don't really think of this as much in software, though it can be used to advantage. And this is where you have a sequence of serial operations to perform, and you can decompose them into per, say, datum or per video or per frame that you need to process. And you can break things into serial stages, okay? And so video decoding and network processing, for example, on a per packet basis fits nicely into this. And I can take each of those pipe stages, say, and implement them onto a separate core. So it's another way of taking advantage of these multi-core systems, right? And then you can combine these approaches in, say, some type of cluster system. So you can, inside of each of these elements that you've mapped, you can put in an entire multi-threaded application, for example. Okay. So in order to do this, though, even building pipeline parallel structures and general parallel structures, programmers are still not very good at it. And they need tools to help them. And we envision building an entire tool chain that starts from identification of parallelism and ends with verification and runtime system support, right? So you can look at it. So here we joined this minority chorus that along with Steve Lametta and Win Mei Hu and a few others, say, look, maybe the best way to write these parallel apps is to really first write it sequentially. Make sure it works, get it right. Then let's look at where the performance bottlenecks really are and try and get those portions of the application to parallelize. Okay, now, this is not always the right way to go, obviously. Scalability can be hard to achieve in these types of environments. But nevertheless, it's something that's definitely worth considering, right? The sequential app also teaches you a lot. How many people here have not learned something about the application they were writing as they were writing the application, right? And so hopefully you'd want to learn those things up front when it's easy in the sequential space before you go ahead and parallelize everything. So what I'm going to we have research in all of these areas. The most mature research is on identification and implementation. What I'm going to focus on today, given some feedback I got earlier, is on the identification of parallelism and really focus on this parameter tool, right? And talk a little bit about the prototype that we're developing for this tool and some of the technology that underlies it. Okay. So one observation is that when you're writing a parallel program, identifying concurrency is hard. Right? Finding out exactly what can go in parallel and what can't is difficult. You might have some intuition as to what these things might be, but knowing what they are for sure is non-trivial. Implementing a parallel algorithm is somewhat easier than this, though getting all the corner cases right is the hard part. Right? So getting something that sort of works is not bad, but then getting it so that you have no race conditions and none of these other problems, that's a hard thing, right? So what we're trying to do with parameters, we're trying to help find large-scale parallelism in existing programs. Now, we're not proposing an automagic approach. So I'm not saying we're going to take a compiler, we're going to analyze your program and extract the threads for you. Right? We're trying to help programmers, not replace them. So we're going to try and point out, hey, here are some areas where you might have some parallelism. You should go investigate it. And then produce the tools that will help them investigate it and maybe prove to themselves that, yes, I can parallelize this application. And then go ahead and write the tools that help them extract these programs. But we're envisioning it as an interactive process. Okay. So we're going to start by looking at parallelism in sequential applications. And people often have misconceptions about sequential applications. And I don't know how many people in this room have these misconceptions. But people say, oh, well, what are you going to do with sequential applications? Clearly, 25 years, 30 years of compiler research has failed. These applications have no parallelism to speak of beyond the fine-grained ILP. But that's not true. Under ideal circumstances, there's been plenty of prior work that have shown that these sequential applications have a lot of parallelism to offer. Right? Executing hundreds of, in fact, being able to execute hundreds of instructions at a time over sustained durations. The problem is that none of this parallelism can really be exploited by instruction-level parallel techniques. And that was shown by Wall in the Digital Western Research Laboratory back in '91, where as soon as you impose limitations on your branch prediction accuracy, you impose limitations on your instruction window size and so on, most of the parallelism is gone, right? You'll never see it. So, but the issue is maybe we can extract that concurrency into threads. The problem is that there's no study to even identify what code is responsible for this stuff, right? And there's a lot of it. So what's going on there? And that's some of the motivation for building up this parameter tool. So what we're going to do with parameters, we're going to try and visualize concurrency in dynamic trace data. Okay? And we're going to look for the basic sources of parallelism using the results of dynamic analysis. And hopefully going forward, we'll be able to integrate with the dynamic analysis, the static analysis to say, well, here are things that I can prove statically will always happen, and here are the things that I can't. And this helps programmers find out, well, let me see, what can't the static analysis prove? Oh yeah, it can't prove this. Okay, but I know that this happens to be true, and therefore I'm going to fix it in this fairly simple way. Or, oh, this is not true, this is not real parallelism, and it can inform the tool, and then you can take that out of the search space. Okay? But the key insight, as we'll see, is that in order to do this analysis, we're going to need an analyzable compressed representation, because the biggest problem that you face here is the size of the data sets that you have to analyze. Okay, so the basic plot that we use in parameter is what we call the DIN versus ready plot. And so what is the DIN? Well, DIN is just a dynamic instruction number. Given a trace, what is its position in the trace? So on the left side here, we see a subset of a trace of a program that computes the Fibonacci sequence. So it's just a toy example, okay? And so because of how we plot this, the first instruction in the trace is down here, and the later instructions in the trace go up. Okay, so what we're going to do, if you look, under non-ideal circumstances, on the horizontal axis of the plot, we're going to plot the ready time, right? When does the instruction execute in clock cycles? Okay? And in the naive case, every instruction executes in its own individual clock cycle, and so you just see this diagonal line going forward. However, under ideal circumstances, no branch worries, no memory delays, no processor width limitations, you can see that you're limited by your data dependencies. And so these first 4 instructions have no data dependencies, and so it can all be scheduled in cycle 1. Right? The next set of instructions are all scheduled in cycle 2 because they somehow depend on the instructions in cycle 1. Notice in these types of plots, by the way, instructions are pushed as far to the left as you can. Because if there were no data dependencies, then it would have moved over even further. Okay? And so we go on like this, and we plot this thing. And if you look, generally, if we were to zoom out on this, you see that these instructions, this forms a diagonal line from lower left to upper right, which corresponds to a chain of dependent instructions, or a collection of instructions that are all dependent on each other as you progress through time. All right, so this isn't by itself very interesting, but now let's zoom out. And so I apologize if this is a little light. We fought with what the best way to represent this data is, and so in a presentation. But this, hopefully you can see enough to see that this is a plot. It's the same plot that you saw before, but for 254 gap from the SPEC benchmark suite, which is a sequential application, right? It's not one of these loopy scientific codes. It's a sequential, serialized application for the most part. And so what you get here is, again, the first instruction in the trace starts here, and instructions are numbered as they go up. And then on the horizontal axis, you have time. If you look at this graph, you'll notice that there are these spidering lines that pop out here, right? These are multiple dependence chains, and they're overlapping in time, which means that they are potentially threads that you could extract and exploit. There may be dependencies from the left thread to the right thread, for example, and that's fine because that forms a pipeline structure, right? If you extract these threads, they'll form a pipeline structure. Now, these are under ideal circumstances, so not all of these things are going to be extractable as threads. So we want to ask the question, okay, well, what are these things? What instructions are responsible for this? What part of my static code is actually executing in parallel here? I don't know. And to date, no one can tell you, right? And the reason is because you have 9 billion instructions here on the vertical axis. You have 150 million cycles, right? Now, how do you keep this data around and do a data analysis, right? The full 56 gigabytes of data are required just to list the program counter locations of all the instructions. Forget what addresses they access, right? Forget about what directions the branches went in and so on and so forth, right? And any summary of the dependence data is going to be huge too. Okay, so how do you store these and how do you analyze this data? And this is the problem that we're focusing on with Parameter. So if you look at what happens today, we have a trace compression routines, for example, by Martin Bircher at Cornell. And if you look at that work, they get really good compression results. I can take that terabyte trace and I can compress it maybe to 50 gigabytes or less. So I have a terabyte of data with all this stuff in it. I can compress it to 50 gigabytes. The problem is to do any analysis, I have to decompress the data. I don't have to keep it on disk, but I have to stream through the entire decompressed representation. 50 gigs of data, it'll take me a minute or so to reach the billionth instruction, maybe a little under, right? To reach the 2 millionth, like 15 seconds or so, just to get there. And then I have to summarize all the information for what came before if I want to do any type of data analysis on this. You have better approaches like sequitur that was originally proposed for compressing gene sequences, and Jim Laris at Microsoft came up with using it for representing program paths. The problem is it's grammar-based, and it's really only good for sequence matching. So I want to find subsequences of code. Okay. Now, using these types of techniques, this compression, and then using a special plot that shows the distance between how far is your ILP. So notice the vertical distance between those two threads on that original DIN plot tell you how far regions where things ran far apart in the trace but are actually capable of being executed in parallel. So looking at that distance plot, we came up and we said, hey, there's this place in this propagate block function in GCC where I can execute a lot of stuff in parallel. And this goes on for a while. There's some cross dependencies that you can implement as pipeline forwarding through pipeline stages, and then there's a recurrence. There's a lot of this stuff. Okay, so that's great. You say, well, there's no problem. Look, I can identify parallel structures in this code. Well, guess what? Craig Zillis, in his papers on speculative threading, same example. Princeton folks, decoupled software pipelining, same example, right? Guri Sohi, I think, in a paper after Craig Zillis graduated, same example. All right, so why is everybody using this particular example in this particular function? Well, the answer is it's really easy to find, right? And the fact that everybody uses it, it's likely the only example you can find because we looked hard and it was the only one that we could find. And we said, look, we have a problem here. If this is all we can find based on all this data that we're able to collect, we really have a data mining problem here. How do we actually look at this data and explore what the heck is going on? Okay, so what we said is, well, we need a better way to represent the data, right? And if you look at it, we want to represent the data and compress it in a way where we can still analyze it. Well, what are the types of analysis we want for finding parallelism? Well, we want trace data flow slicing, right? So we want to be able to look at, here's a set of instructions. Who needs their values? Show me who needs their values. Right? That's a forward data slice. Show me where these values come from. That's a backward data slice. Because this is going to give you insights on which dependencies you need to break to improve the amount of parallelism available in your program. Okay? You want to do control flow slicing to find out where the control flow is really limiting what you're trying to do here. Right? You want to also be able to visualize things like do the trace visualization. You want to visualize these slices. You might want liveness information to find out, well, if I parallelize these two things, how many data values do I need to keep live before I can, so that the later computations can use them? That's important. If I need 50 gigabytes of RAM to keep my data sets live in this parallelization, that's probably not a good idea. I'm going to have to swap to disk, right, on most systems. Now, maybe in 5 years I won't have to because RAM density will double, but fine. There are still other applications where you can think of this. So what we're going to do is we're going to represent traces using a set-based representation, and in particular use a compressed form of binary decision. We're going to take Boolean functions. We're going to take traces, represent them as sets, take those sets, represent them as Boolean functions, and then take those Boolean functions and represent them as binary decision diagrams, right? So that's the chain. So let's start in this chain. And as we'll see, we get good compression, and the analysis on those decision diagrams is relatively fast. So let's start. So first we need to understand, how do we represent a trace as sets? This is based on the idea of characteristic or indicator functions. So I have this function here, phi a of x, and we say that this function is equal to 1 only if the element x is in the set A. So if we have a set A and it has dog, cat, snake, ferret, whatever, and we say phi a sub a of cat, well, that will be 1 because cat is in the set. But if I were to choose, say, iguana, phi of a of iguana would be 0. And we see that this function is called the characteristic function of the set A because it tells you what's in and what's not the set. It uniquely characterizes the set. Okay, so now let's take an example of how we do this with trace data. Well, we have our dynamic instruction number, which is just a number from 0 to, say, 2 to the 64, minus 1. And we have our program counter location. In the most basic sense, what is a trace? Well, it's a list of program counter locations that you executed. Okay, so all we do here is we say, well, if we had the set of tuples of all program dynamic instruction numbers and program counter locations, we have a trace. So program counter value 0, right? PC value 4, 1, 5. And we can extend this as far as we need to go. Well, in this case, now this is a set. This set A corresponds to a very, very simple trace. Okay, great. What's the indicator function for this? Well, phi of 0, 4 is going to be equal to 1. Phi of 0, 1, 5 is going to be 1. And phi a of anything else is going to be 0 because there's nothing else in our set. Right? So is this clear? Because if I move on and this is not clear, then all is lost. So hopefully this is clear. Okay, great. So, whoops, excuse me. So now, how do we represent sets as Boolean functions? Well, this is pretty straightforward for people who haven't seen it before, but I'll take a little bit of time to explain it if you haven't. Right? So if you're in the PL space, I suspect that there are a lot of things that look a bit like this because people have done work on using binary decision diagrams for analysis, and so you've seen it. But if not, So if we have a set A, that's the same set that we had before, and we know what its indicator function phi sub A looks like, we can represent it as a Boolean function by encoding the elements using a Boolean representation. So let's say that my dynamic instruction numbers can range from 0 through 8. Well, then I need 0 through 7. Then I need 3 bits for my dynamic instruction number, and I'll call those bits, I'll call that vector x, right? And then my program counter, I'll have a 3-bit vector called y. Okay, so now I can encode 0, 4 as a tuple on these variables as 0, 0, 0, 1, 0, 0, right? Pretty straightforward. Any questions so far on this? All right, so pretty straightforward. 1, 5, I can do the same thing. Now I take phi a x, y. Well, what does this look like? Well, I just encode as a Boolean function, right, the fact that x2 is 0. So this first term encodes 0, 4. Well, x2, x1, and x0 are all 0. So it's not x2, not x1, not x0. Right? And I do the same thing for the other things. Now, if I plug in into this equation 0, 4, well, what do I get? That's 0, so that's a 1. 0, knotted 1. 0, knotted 1. 1, not knotted, that's a 1. 0 knotted is 1. 0 knotted is 1. OK, so these are all 1s. This conjunction turns to 1. And therefore, the characteristic function evaluates to 1. So I know 0, 4 is in my set. Pretty straightforward. OK, so we can do other trace data in this way, too. Right? We want the data dependence graph to do slicing. No problem. Right? That's just a set of tuples from E goes V cross V, where V are the vertices. Well, the vertices, what are they? They're the instructions, which we can represent uniquely by their dynamic instruction number. Right? So done. Din versus ready time, that graph that we saw earlier, same thing. The ready time is just another number. Okay? And pretty much any arbitrary data can be encoded in this way. Now, we want to compress this data into a compact representation for which we use a graph data structure called the binary decision diagram. And the binary decision diagram works as follows. The best way to think about it, these were proposed by Randy Bryant in the mid-'80s and have been used extensively in hardware verification as compact representation for Boolean functions that represent transition systems and graphs, right? Which is exactly what we're trying to represent here. So now I have a tree here. Okay, and this is just a Boolean tree for some arbitrary function in 3 variables, x, y, and z. The way I read this is I say, well, what is the value of the function for x equal to 0, y equal to 0, z equal to 0? Well, I just traverse the left edge of this tree, right? The open circles represent the arcs that correspond to when that variable is false. Right? So now I just traverse the left edge and I find, oh, f of 0, 0, 0, well, that's 0. Right? But if I change the value of z to 1, I get 1. Okay, so this is a graph structure, but the problem is we all know this is exponential in the number of variables. So we want to compress this representation down. So what we're going to do is we're going to convert these trees into what are called reduced ordered binary decision diagrams. By ordered, I mean that for every level in the final graph, that level always corresponds to the same variable. So in this case, the top level corresponds to x, the middle level y, and the bottom level z. And that's called the ordering. So the ordering here from top to bottom would be x, y, z. Now let's compress this into a binary decision diagram. First thing we notice is there's no reason to store a node that represents the same function twice. 1, the constant function 1, we only need 1 node to represent 1. So we're going to combine all the nodes that used to go to 1 into a single node 1. Right? And all the arcs are going to be redirected there. So we can do the same thing for 0, and we get this particular graph. Second observation is there's no need to have a node if both the true and the false arcs go to the same function. In this case, notice that this true and false arc go to this function, 1. So it doesn't matter what the value of z is once you get to this node. Right? x0, y equal to 0, and I'm missing a circle, I apologize. Y equal to 0 goes here. Well, they both go to 1, so who cares what the value of z is? I can remove those nodes, so I'm going to eliminate them. Okay? So I eliminate those nodes, and I end up with this particular graph here. The third optimization that you perform is to observe that if there's a function and its complement, there's no reason to keep both those things around either. I can just mark an edge as an inverting edge. Right? One way to look at this is that this is a multiplexer. These are the control signals on the multiplexer. And so I just multiplex one of these signals up, and I go through the tree, and at the output I get one value. right? Well, I can also just stick in an inverter and not have a multiplexer tree that just has the bottom elements flipped around. So if I do that, observe that this function and this function are opposites of each other, right? They're inverses. So I can eliminate one of the nodes. I can eliminate one of the nodes. There we go. So I can eliminate one of the nodes, and then I mark the false edge as inverting. Now, just like you can form, just because you have things like and not are complete, and therefore I can represent or using nots and ands. Similarly here, we have a problem that there's once we introduce these inverting edges, the graph for a particular function is not unique. But we want to keep this representation canonical, which means that, because it's important for our complexity results. And so what's been proposed in the literature is to say, well, only the false edges can have these bubbles on them. And if you do that and you think about it, it turns out that then every graph is unique, and you can represent every function. So notice that 0 and 1 are inverses of each other as well. And so we'll eliminate them. And then redrawing the graph a little bit, we end up with this BDD. Now, because BDDs are canonical, it turns out that, say I have the constant function 0. It always has the same representation, which is just the constant, it's just an inverting pointer to the constant node 1. Okay. So what does this tell you? Well, if you're paying close attention, what this tells you is it must not always be possible to build these BDDs efficiently. Because if it were, I could solve the satisfiability problem simply by encoding my SAT problem as a BDD, finding out that it's a 0 node, and saying it's unsat, right? And then P would equal NP, right? And I'd be accepting my Turing award right now. So, or Randy Bryant, whoever proved that this were the case. So it turns out that not all data has good BDD representations, okay? And in particular, these can blow up exponentially. So what we want to see is in practice for our trace data, are they a good fit? Okay? And it turns out that this problem is complicated because the ordering heavily controls the size of your resulting BDD. And you have to come up with a good variable ordering for the problem at hand. So here, if you notice, this is an order where z is on the top and x is on the bottom. And this BDD is the same function as this BDD, but it only has 3 nodes. In general, as you have more variables, the amount of compression that you can get can be exponential relative to the truth table, or you can be on the linear in size of the truth table. And so you want to be on that exponential compression side and not on the linear side. Okay? So what we've done is we've done a lot of work to come up with what is a clever ordering, and I won't get into the details. I'll be glad to answer questions onto what the clever ordering is and what it's not in this case. But with this particular ordering, we're able to store so what we see on the graph, the vertical axis shows how many tuples of the data dependence graph for a trace we can store, right? Because that's interesting information. The DIN, PC, okay, that's less interesting. We can store a lot of those too, but this is an interesting piece of data because it's derived data that's hard to come by normally. And the vertical axis shows how many of those tuples we can store. We're storing a 64-bit value for each side of the tuple, x, y. So each of these naively is 16 bytes large, okay? But in a gig of RAM, what we see in the black bar is how much we can store in a gig of RAM. How many of these can we store? You can see in the peak case, we can store almost 4 billion instructions in 1 gig of RAM, okay? On average, you're getting around 1 billion instructions per gig of RAM, right? This is a 16 times to 60x compression ratio. It's pretty good, right? It's not great. There are compression algorithms that do better. But remember, the purpose here is not to get the best possible compression at any cost. The purpose here is to come up with a compressed representation that's also analyzable. Okay, and so that brings us to the next result. So we said slice analysis is an interesting analysis. So let's look at slicing. If we look at slicing, here's a fragment of the data flow graph. Okay? And here is a pseudocode for slice analysis as performed on BDDs. And let's go over this and see how it works, and I'll highlight the important complexity results. Okay? So a blue node is a node. So what I'm going to do is I'm going to build up the dependent slice for a set ID. So ID is my initial set. And these are a collection of instructions. And I'm going to find out what are all the instructions dependent on this instruction. Okay? That's the goal. That's forward slice analysis. So ID is an initial set. And so if the node is an S is the slice set. So it's the forward slice as I compute it. And at the end, S is all the instructions that depend on ID, including ID, okay? So let's start. We start at the algorithm, and S old is equal to 0, fine. We're not really worried about that right now. So it's the empty set, right? And we start S as ID. So what is ID? Well, I'm going to pick a node here arbitrarily to be ID. And so S starts out as the singleton node right here. Notice that it can be a set of nodes, however, and the algorithm functions just fine. Internally, we'll see that we create sets of nodes. How do we represent sets? Well, we use BDDs. So don't forget, every one of these variables, ID, it's represented using a BDD. S, it's represented using a BDD. Everything all the variables we construct in here are BDD variables. Okay. So now, what I do is I need to compute the output edges. So I have the set of tuples and I have the set of states. And it turns out that if I intersect them, the set of edges with the set of initial, I call them states because that's what they, always in the hardware verification world, they're called states, but they're instructions here. If I take the intersection of E with the set of instructions that I'm worried about, it turns out that I get the set of outgoing edges from that, okay? And so I get the set of outgoing edges. Well, these are on BDDs. How long does that take? Turns out the operation is polynomial time in the size of the binary decision diagrams and can be reasonably fast. Now, saying that it's polynomial time is a little bit deceptive because these BDDs are large. And so it can take some time. But it's still much, much better than streaming through the decompressed version of the trace, right? And I'll give you an example. I'll show you some results where it shows that the actual times that these takes are reasonable. Okay, so that's polynomial time in the size of the BDD. Next thing I have to do is, well, I have the edges, but I want to find the output nodes. So this existential quantification here, what it does is it strips out the first part of the tuple. Right? If I have the set of edges that lead to where I want to go and I strip out the source, the destinations are the first set of dependent instructions. Right? So I strip those away and I add to S those nodes. So I get these new nodes in my set S, right, my forward slice. After this, I do a rename operation which you need for technical reasons because I have the second half of the tuple and I need to rename everything to get the first half of the tuple so that I can repeat the computation, right? So I do that rename. Then I say, did I add more nodes to my set? Yes. Okay, try again. Right? So now I compute the next frontier slice. So I do it again. I find the outgoing edge set. But now notice that S is a set of nodes. E is still my total edge set. I do the intersection, and I'm going to get a whole bunch more edges. Okay? And note, the complexity of the operation is the same. It doesn't change. It's as complicated as it was before. So now I do that, and I'm going to get a whole bunch more nodes. Okay? And I'm going to say, did I add more nodes? Yes, I did. So you go again, and this time I didn't add any new nodes, so I'm done, and I return S. This is the forward slice computation, right? So this is pretty simple. All these operations are polynomial in the BDD. Some of them are really cheap. This is linear in the number of variables I have. This operation can be, and the other operations can be pretty fast. The check here, are things equal? Because BDDs are strongly canonical, it's constant time. I just compare, are the two pointers the same? No? Then they must point to different functions, which means the sets are different. So it's really, really simple. Okay. So I do this, and the comparison to make here is that doing slice analysis on BDDs takes a few seconds for a gig of RAM. Doing them on the compressed trace and streaming through to find the slice can take minutes. That's a big, big difference, right? In particular, for a particular case, if you look to, say, take the 2 millionth instruction, right? And to compute the forward slice of 2,000 instructions takes under 2 seconds using our approach. Just streaming and finding the 2 millionth instruction in a normal trace takes over 15 seconds, okay? And so if you do the 2 billionth, these things scale. The old approach is linear, so now I have to take 10 times longer, 150 seconds. Our approach, 2 seconds, right? So we're really good for the analysis once you can build the BDD. All right. So in summary, sequential programs have a lot of parallelism, despite misconceptions. But no one knows what that parallelism really is. And we're trying to figure that out. So parameter gives you visualization and analysis of large traces to help us find where that parallelism is. Now, I really wanted to have a demo of the tool here. But you know how things go in software development. We have bugs, and it's a little clunky right now. So we're working on it. I'm hoping in the next month or so we'll be able to have a good demo that shows interactive visualization of traces, and then get some really cool results on how to parallelize applications. As I said, I really wanted the demo here, and I apologize that, well, you know how these things go, right? How long has Gmail been in beta? Right. So, in summary, we get 16 to 60x compression, and we get analysis without decompression. That's a key factor, right? No decompression for analysis. The complexity of the analysis in terms of the compressed size, not the decompressed size. Okay? So this translates to seconds versus minutes for slice analysis. So in general, where's this going, right? How can you use this? I told you these threads look like pipeline parallelism. What does pipeline parallelism get you anyway? So let me give you an example of some work that John has done. We're looking at network processing, and we're trying to process, say, gigabit Ethernet frames, and you're trying to subvert denial of service attacks or something like this. Well, in these scenarios, you need to process every gigabit Ethernet frame, and you want to do it at line rate with no drops, right? That's ideal. That means you got to process 1.488 million frames per second. Right? That's a lot of frames that's coming in. They're small. They're 64-byte frames. You're not bandwidth limited in this process. But what you're limited by is the overhead of processing each frame, stripping the header, finding out where it comes from, so on and so forth. Right? You have, at that rate, 672 nanoseconds per frame, 1,200 clock cycles. Main memory, how long does that take? One access to main memory, right? 100 cycles, right? 200 cycles. A system call will cost you 200 cycles or more, right? 600 cycles in some cases, 1,000 in others. Okay? So it's higher and higher, right? So that's not a lot of time. And in fact, it's not possible, as far as we can tell, with one processor to achieve this. But you can build a pipeline structure and really accelerate this. So what you do is you break up the application in 3 stages, which is what we've done. You have the input phase, which deals with the network controller and pulls packets in, frames in. The app phase, which actually does work on them. And then the output phase, which blasts them back out. Okay? Now, a cool thing about this, and I don't have time to talk about this, this input stage runs in kernel. This application stage can run in user space. It doesn't have to, but it can. In any case, by doing this now, each of these stages gets dedicated a processor, and then I just run frame after frame. Notice once the pipeline gets going, so this is time on this axis. I forget I'm an architect, so I think everybody knows how to read these diagrams. This is time on this axis. On the vertical axis is frames that we're processing. On the frame axis, on this axis, notice that this frame still takes time t. It doesn't get any shorter. The latency is the same. But our throughput is tripled. And the reason is because once this pipeline gets going, right, notice I can overlap app and IP. Here I'm overlapping the input, reading one packet, while I'm processing the previous one, while I'm outputting the one before that. Okay? This is built in software. We have a working implementation. Hard thing here is that you have to transmit data from these guys to each other really fast. We have a mechanism with no special hardware support on commodity hardware, can do that transmission in 35 to 40 nanoseconds. That's really fast, right? I mean, I can say it, but think about it. 35 to 40 nanoseconds, that's less than the time it takes to access main memory. Right? And we have a clever way of arranging the caches and using prefetching to overlap the transfer of data with other useful work. Okay? And so with this, as far as we know, on a dual-core, dual-processor AMD Opteron system, we can hit the full, well, 95% of the full frame rate. We can probably do 100%. The reason we don't know is because our network cards can't generate 100%. So all you do is you attach a kernel module, pin it onto a process, and tell it, blast packets out of this network interface. We can't get up to a gigabit. So we're at 95%. I don't see why we shouldn't be able to go to 100%. Right? Really good. This is pipeline parallelism. And it's a mechanism of using pipeline parallelism for performance benefit. So in conclusion, unit processors are at the end of their life. And we need to utilize multiprocessor systems. We happen to think that pipeline parallel systems are a good way to do this, but there may be other types of parallelism. But programmers, in any case, need a tool chain to help them identify parallelism, implement, verify, and verify. And finally, you need runtime system support. For example, we need to be able to have a user space application have a pipeline stage in the kernel that's pulling things from the network. That's one example of runtime system support. And we're working on all of these areas. You've seen parameter. I briefly described fast forward, which is that high-speed communication mechanism, right? And then we have work in these areas, which I'll be glad to talk about. These are much less mature than the first two, though. So that's all I have to say. Are there any questions? I think I went a little over time, and I apologize.
I'll get us started with the question, and I'll be passing this microphone around if you want, so we can get questions for the remote office in the video. So the pipeline parallelism example, if you took a bushel of smart engineers, you probably 2 or 3 of them would have tried that themselves. So can you explain a little bit more detail what the parameter system would, how it would help them in improving that above and beyond the basic intuition of tri-pipeline parallelism?
You mean the network application?
The pipeline example you showed.
So the network application. So I think that there are applications for which it's a no-brainer to figure out the pipeline structure. And in that case, why run parameter? Right, there's no point. There are other cases where it's a lot less clear how you can build pipelines. So one of these applications that we're looking at, and we're not doing it with parameter actually, but is looking at certain scientific codes and seeing if we can speed up the core kernels that are not parallelizable or hard to parallelize, and seeing if we can parallelize them using a pipeline structure. But there are, the best work to point to is work out of, say, Princeton University, where they are automatically pipelining code in tight loops. And it's really hard to see. They build the data flow graph, they partition it into strongly connected components, and each of those strongly connected components becomes a thread. It's really hard to see what that parallelism. Parameter will show you that parallelism, and it'll show you parallelism that's coarser grained than what they're able to find in that particular scale. For example, this propagate block, and it escapes me now what GCC is doing there, but if you look at propagate block and what's going on, looking at the code, you wouldn't say, oh yeah, duh, I can parallelize it. But when you look at it after the fact and you see what it's done, you're like, oh yeah, that's pretty clever. I could parallelize it in this particular way. So it's hard to give examples until we have a working tool, and we'll gladly publish a paper. But certainly our hand inspection has shown that there are structures that are parallelized in there that you think, what? How is this going in parallel? And then you realize, oh. Now there are shortcomings to parameter, right? One of the reasons parameter won't show you the networking examples parallelism. And the reason is because it's an application level tool. But notice what we've done. We've overlapped OS services along with the application. So it's something that we would like to extend. So notice that parameter has its limitations, but it also has its strength. It's going to show you these things internally that are difficult to find. Yes?
How do you handle the memory dependencies in the trace?
Oh, when we record the trace, we log the addresses that are actually read and written by every instruction. And then when we build the dynamic data dependence graph, we keep that into account. To build the dynamic data dependence graph, we run through the trace, and as we do that, I have this inverted page table implementation that so that it can keep around all the dependencies in some type of reasonable way without having, I can't have a 2 to the 64-bit flat array. So I use an inverted page table and some clever algorithmic hashes in there. I have 2 levels of hash, and it'll help me track the dependencies as I go along. So that's how it's done. I can even ship you the code if you're that curious about it. It's not that bad.
So it appears to me that the compiler should be able to resolve most of your dependencies anyways. For example, if you have regular loops or with no loop carried dependencies, you get like really long traces, but the compiler knows exactly what's going on there. Mm-hmm. So any plans of incorporating that kind of information?
Well, okay, so there are 2 questions in one there, right? So the question was, the compiler knows a lot about the dependencies. You get these really long traces, and the compiler knows 90% of the time, maybe not 90%, but for a bulk of the time knows what's going to happen there. So the one question is, can you use this information for compression? And the answer to that is yes, but it's not clear to me yet how that would affect the analysis routines, right? So if I use that information in compression, would it complicate the analysis? I don't know. Would it lose certain granularity to be able to pull apart the structures I summarize? I don't know. So for compression, we've thought about it, but so far I've stayed away from it because everything I showed you in terms of these representations is naive. It's the first cut. And there's a lot of research in how to make these representations even more efficient that come from the hardware world that we want to map in. So on the compression side, it might be a while. On the help the programmer figure out what to look at, what he or she should look at, on the other hand, we are planning to use static analyses. The biggest obstacle is because of the scale that we're looking at, pointer disambiguation is really, really important. And the existing pointer analysis techniques are decent. So we have something coming online on that front, hopefully soon. We have the pointer analysis working and everything, but we don't have the two tools integrated together. So once we integrate them, hopefully we'll get some data. Going forward, then you need better pointer analysis, and we're looking at combining point-to analysis with abstract interpretation to help resolve some of these details. That's still in its infancy.
Good luck with that.
Thoughts. What's that?
Good luck with that.
Yeah, but well, if you look, so the reason why we think it's promising is because pointer analysis can be cast as abstract interpretation problems. And that's why we think, well, maybe you can actually combine different abstract domains and actually do things with them. Doing it in the large is the hard part.
Another small question is, in your experience, how do you see any correlation between ILP and TLP, such that if you have applications with a lot of ILP, those are your prime candidates for TLP or anything?
Okay, there is a tight relationship in certain cases between, so the question was, is there a relationship between ILP and TLP? And in certain cases, there's a tight relationship there. So some anecdotes about people doing automated compiler analysis to extract some of these pipeline parallel structures. And it turns out you have to very carefully balance what you consider ILP and what you consider TLP. Because otherwise, you can do a threading where you steal all your ILP into TLP, and then you're not really utilizing the processor core itself very well, and you gain almost nothing. And you have a much more complicated program to boot, and you're using two processors. So you have to be careful not to take away things that the processor is good at executing as ILP and then turning it into TLP. That's useless. You have to make sure that you're grabbing the things that the compiler wouldn't be able to get from ILP. Parameter will help you do that because it shows you this distance in the trace. And it can show you the control dependencies. And so you can say, well, what is likely to be extracted as ILP and what is not? And then you can help pull those things apart in that way. But it is a point of concern, and if you're not careful, you end up doing these useless parallelizations.
Can the tool be used to show me that I may have some parallelism if I can break this particular dependency?
We don't have a good visualization for that yet, but yes. And in particular, what you can see by doing the slice analysis and slice visualization is you can see that there's this very narrow thread that all converges on one point. In fact, if you zoom in onto some of these graphs, and if you recall the paper we presented at EPIC 3 maybe, or EPIC 4, we showed that there are these critical dependencies. And in that DIN plot, you can see there are these critical dependencies where all these computations converge to compute this one value, and nothing else can happen until you compute these like 1 to 10 values, and then everything diverges. So you can already see that information. What we want to do is have these what-if scenarios and a visualization for it. You say, well, what if I were to break it? What would happen? And then if it just backs up by one cycle because there's now some other critical dependence, well, then you know, okay, maybe that's not so good. On the other hand, if you could break it for real, you might get a lot more parallelism out of it. So we're working on that, but first we had to get the initial stuff up and running. So yes, but it's not there yet.
Any other questions? Okay, one last question.
I've worked on kernel tracing. So we have a tool called the Linux Trace Toolkit Viewer, which is basically using this tape format, uncompressed data. But, well, we do time-based indexing of this data and periodically dump, well, in that kind of scenario, that would be, let's say, for periodically we would dump for all the variables, we would say we keep track of the last accesses, and this helps us seeking quickly in the data. The comparison you've done between your compressed format and the tape-based approach. I think it's based on the fact that you have to stream along all this data before you can get to the actual data that you need. So what are your thoughts about, well, having this kind of fast seek in the raw data? Would that diminish the difference between both approaches?
So the question is, you can store these traces using time indexes so that you can randomly index into subparts of the trace, right? There are these fixed points, sort of like, what are they, the P frames or the I frames or something in MPEG video, right? You can jump to any of them. Okay, so my feeling on that is as follows. As far as the example I gave, it would make the example less compelling, certainly. And so in some sense, it's not a fair comparison that I gave. On the other hand, the general principle, so there are two issues with having these time index databases. One is that there's a limit to how much you can compress them, okay? Because you can't compress across that time index. Because if you do, you can jump to the time index, but you can't decompress from that point forward, right? So you can't use previous things. So it limits the rate of compression. And it's really important for interactive analysis to get the bulk of your data in RAM. Or you just have a giant cluster behind you, and then you click on it, right, which is the case that you guys have. The problem with the giant cluster scenario is that I want to often do analyses of my analysis results. And in this case, when we build you do a slice analysis, we build a BDD of that. And you can just treat that like another trace and now do all your analysis inside there recursively, which is a useful thing. And the time indexing doesn't really help you do any of these types of things, right? And the big cluster behind you also, once I have a slice and I want to do things really fast on the slice or work on a lot of instructions at once to figure out what's going on, the time indexing thing, even with the big cluster behind you, is not going to be competitive with something that's an in-memory approach on one workstation. Now, having said that, there are analyses where the time index database and having the cluster behind you is actually better than what we're proposing. So, you know, you'll get, I'm not going to say that it's the be-all and end-all of everything, but it is very good for a large class of analyses that we want to do, right? Because we do have some clusters at CU where we can you know, get maybe not hundreds, but not thousands, but hundreds of, you know, 100 machines or 100 processors working on the problem. And it's not clear to me that that's going to really get you what you need all the time. So does that answer your question?
Well, basically, with the time index, what we can do is whenever you seek to a precise location, then you have, well, all the data about the state of the system at this moment is supposed to fit in memory for quite large traces if you have a limited set of variables.
Right.
And then the information you're interested into is located between two consecutive time intervals. So basically, there's no real need to have a cluster behind you to deal with that.
So that's an example of analysis where you have time windowed analyses, right? Where you don't even need a cluster and the time index database is pretty darn good. We're not bad in that case, but if that's all you're doing, the time index database is actually better, right? If you're trying to do, what we're trying to do is look at the program as a whole, because we're trying to pull different pieces from very far apart in the trace and then try and parallelize those. And in that case, we've tried the time index database, as I said, and in that case, they leave a lot to be desired. And they don't scale very well with, let me look at a whole set of things. Let me look at even more and more. And you eventually start pulling in, you need little chunks of tons of the little pieces. And that's where a cluster will help you, right? But it's still not as competitive as this approach. So, as I said, there are pros and cons to all of these things.
If people have other questions, I believe Manish is around this afternoon and has some time to talk with people. If you're interested, just come up and let us know. Otherwise, let's thank Manish for the interesting presentation.
Thank you guys for attending.